You can ask questions. Just the audio though. All right, guys. So today we're going to be looking at how do we graph translations of the sine and cosine function. Now, translation just means that you're going to be altering the sine and cosine. So let's just do a quick review. We don't have to graph it, but let's just talk about sine and cosine for a second. So the pattern for sine is sine starts at 0, and then it goes up to 1, then to 0, then to -1, then back to 0. And it just continues on indefinitely. So that's the pattern for sine. The pattern for cosine is different. It starts at 1 and then goes down and then goes to, starts at 1, then it goes down to 0, then to -1, then back to 0, then back to 1, and then, of course, it just repeats itself and oscillates over and over again. So those are the pattern for regular old sine and cosine. But what would happen if we translated or changed or altered those graphs? And we're going to be looking at two in particular today. We're going to look at amplitude, and we're going to be talking about frequency and period. Now, last time I checked, Mr. Loeb, if I have an amp in my car and I hook it up to my speaker system, what am I going to be doing?
Boom, boom.
Boom, booming, right? Because we know that amplitude affects the volume. So when we think about amplitude, what's happening is amplitude, when we make a change like that, it's going to change the height or the maximum or minimum values. So, yeah, she's listening to Beyonce right now. Right, Ms. Thomas? That's right. That's right. All right, so let's take a look at the definition for amplitude. It's on the next slide. So here's the definition of amplitude. The amplitude of your sine function, physically speaking, is how far above and below the middle of your graph it goes. So like regular old sine and cosine achieve a maximum value of 1 and a minimum value of -1. So their amplitude is 1. But if you look at the graph that we're looking at right here, it doesn't reach a maximum of 1. If you look at the graph, this graph reaches a positive, looks like it's a positive 4. So let me go, it goes maximum 4, and then it has a minimum of 1, 2, 3, looks like it's -4 also. So then that would tell me that the amplitude of that function is going to be 4. So the amp of that function is 4. So that's just using the definition of what amplitude is. Now, I probably should have talked about this for also. I bet that I can determine that this is a cosine function graph because if you remember the pattern, cosine starts at the maximum, or 1. In this case, it starts up here at 4. So it's still a cosine function, not a sine function. Now, in terms of where that shows up in a function, if you look up there where it says y is equal to a sine of x and y is equal to a cosine of x, if there's a coefficient in front of the sine or cosine, that is the letter A. Now, don't get that confused with amplitude. Technically speaking, amplitude is defined as the absolute value of A. So, for example, if you had y equals, let's just say, -3 cosine of x, the amplitude is not -3. The amplitude would be the absolute value of A, and A in this case is -3. So the amp of that would be 3, which means that it would approach a maximum value of 3 and a minimum value of -3, as opposed to regular old cosine that goes to maximum of 1 and a minimum of -1. Now, another definition of it, it says the amplitude can also be described as the absolute value or the absolute distance of half of the distance between the maximum and the minimum values. But as Ms. Thomas is showing you right there, I think if you just draw it and look at it, you can see that the amplitude is the same distance from the middle up as it is the middle down. All right, let's take a look at an example right quick. So let's say that you had these two functions. So you've got, it says state the amplitude for the function y is equal to 4 cosine of x. So the first thing I'm going to identify is the fact that A in this case is 4. So since A in this case is 4, that means my amplitude would be the absolute value of that number, which, ironically enough, the absolute value of positive 4 is still going to be 4. So that means it's got an amp of 4. So in other words, when we draw our graph, we're not going to go to a maximum of 1, but we're going to go to a maximum of positive 4. And we're not going to go to a minimum of -1. We're going to go to a minimum of -4. So this graph is going to oscillate between positive 4 and -4. Now, the pattern is still going to be the same. It's still going to start at the maximum, then go to 0, then go back to the minimum, which is -4, then 0, then up to positive 4. And so there's the pattern for that graph. Now, just to kind of show you how that relates to the regular old cosine, it says graph cosine on the same graph. So it would be the same image, it would just be smaller. And so as Mr. Logue just said, he'd be turning up that volume, cranking it loud to
boom, boom.
Boom, boom, pow. Boom, boom, pow. Got to get that boom, boom. All right, so anyway, so then the orange one would be, it would be the same note, but it would be a whole lot louder. So that's the difference. But that's how you would approach that problem. But notice it's the same pattern, it's just louder.
So you're saying that the blue line would be a lower volume than the red line?
It would be. And even more so, think about it like this. If the blue line is your regular cosine graph, right?
Mm-hmm.
4 is our coefficient. So if we took each of those values in the blue, like it's at 1, 0, negative 1, 0, 1, if you took each of those values and multiplied by 4, you would get the orange graph also. Because you'd get 4, 0, negative 4, 0, and 4.
So one might say it's 4 times as loud.
That's true too. It's 4 times as loud. So you're going to be 4 times as deaf when you're 90. All right. So moving on, that's usually the easy of the two. The harder one that people struggle with is the period. Now, let's just do a recap. The period for sine and cosine. How long does it take for sine and cosine from start to finish one of its pictures? Well, if you go back and look at your notes, we said that was 360 degrees. Well, technically speaking, that is 2 pi in radians. So you can change the period, and if you actually change the period, that's actually how you change the note. So every single musical note that you can think of has its own frequency, its own period. A higher pitched note, so a ah, I should have did that. Miss Thomas, why don't you do that note? Wow. Okay. All right. So,
Oh, you wanted higher.
I did want higher.
Okay, Mr. Logue, you hit
There
it.
you go.
There we go.
Now, his pitch would obviously have a lot more waves, so it would be a higher frequency as opposed to Miss Thomas's, which would have a longer, and so that would be the two pitches. So those have different, and notice we didn't change the amplitude. The amplitude is a different scenario. That's going to change the max and the min of it. But here's the formula that we use to find the period. And the most common mistake is that people think that K is the period. You don't. K is not the period. We use K to help us get the period. So the period formula is 2 pi over K. And so we have to identify what K is to help us find the period. People think, well, where does the 2 pi come from? It goes back to the fact that the original period for both sine and cosine are 2 pi. So notice where K is in the formula. It's attached to whatever your variable is. I know we use theta, but everybody could use x if they wanted to, or t, whatever they wanted to. So let's just write an example right quick. Let's say if we got y equals 3 cosine of 5x. So here's the thing, just to review, the amplitude would be the 3. Technically speaking, the absolute value of 3. The 5 would not be the period, right? The period is the formula 2 pi over k. The 5 is k. So then if we plug it into the formula, we'd have 2 pi over 5. That means that the period of that function would be 2 pi over 5. In other words, what that means is from start to finish, it takes 2 pi over 5 units for it to complete one of its pictures. And so that means it's finishing a whole lot faster than the regular old cosine or regular old sine. All right, let's take a look at another example. All right, so for this one, it says state the period for the function y is equal to cosine of theta over 2. Now, notice the understood coefficient in front of the cosine is a 1, which means the amplitude is a 1, so that hasn't changed. What I wanted to see here was state the period. Now, the most common mistake that people do here is that they think the period is 2. They would definitely be wrong. The period is not 2. Even more so, the value for k is not 2. If you remember from, I guess, Algebra 1, if you have, x over 2, that's the same thing as 1/2 x. So theta over 2 would be the same thing as 1/2 theta, which changes the game because now k is not 2. K is technically 1/2. And so that's our value for k. Now, don't get that confused. That's not our period. That's still not our period. That's just k. So we're going to use k to get our period. So we're going to have 2 pi over 1/2. And then just to review our little stay change flip method, we're going to have 2 pi times 2 over 1, which means that would be 4 pi. So the period for that function would be 4 pi. And now let's compare that to what cosine looks like. The period for regular old cosine is 2 pi, which means that this graph is taking a whole lot longer to finish its image than regular old cosine. So if you were thinking about this like what Ms. Thomas was saying a second ago, her 4 pi would be her low. And my 2 pi would probably be a little bit higher than what her node is right there. And so let's actually just do a blank page and just graph these so they can see it on a graph. Can we just do it right? No, we really can't. Huh, didn't know that. Yeah, okay, that'll work. And we can trash that.
Yeah.
It's a beautiful day in the neighborhood. Beautiful day in the neighborhood. That should be mine.
Okay.
Okay. All right. So let's say that, okay, we want to graph both of them. So let's start off by graphing regular old cosine.
Let me see if I can get this off right here.
Oh, the text bar.
Yeah. Aha.
Perfect.
Okay. Sorry.
Okay. All right. So let's graph regular old cosine, and let's do it in radians since we're talking in radians anyway. So regular old cosine goes to a maximum of 1, and it goes to a minimum of -1.
Are we going to be changing the amplitude too?
Mm-hmm.
Okay.
I think the amplitude was +1. Yep. All right. So then cosine starts at 1, and then it goes down to 0, and then down to -1, then back to 0, then up to 1. And so there's the pattern for regular old cosine. And let's label our x's so that we'll know that it's like pi over 2, and then the next one's pi, and the next one's 3 pi over 2, and the last one is 2 pi. All right, so that's regular old cosine. Well, if you remember on the last problem, we changed the period. So it's not going to start to finish in 2 pi. It's going to start to finish in 4 pi. So what we can do is we can probably just change colors and then go out. 2 pi is about halfway. So if we go double up on this side, 4 pi would be way out there somewhere. And then here's how we like to look at it. So 0 to 2 pi, it's start to finish, it's 1, 0, -1, 0, 1. Well, this new graph in green is not going to start and end at 0 and 2 pi. It's going to start and end at 4 pi. So it's going to still start at 1, but it's going to end at 4 pi all the way at 1. Okay, now if you look at the red graph, at halfway, which is pi, where's cosine at? It's at -1. So what's halfway between 0 and 4 pi? It would be 2 pi. So that would be at -1. And then go back and look at the red graph. Halfway between 0 and pi, it's at 0. Just like halfway between pi and 2 pi, it's at 0. So what's halfway between 0 and 2 pi? Be 1 pi. And then halfway between 2 pi and 4 pi would be 3 pi. And that's at 0 also. And so in green, you'll see it's the same pattern, but it's just extended out. And so actually, if you would continue graphing the pattern for red, you would notice that in red, it would oscillate twice, as opposed to green would only oscillate once. And so then that will be the difference. It's still the same pattern, it's just one's moving at a higher frequency than the other one. I think that's it for that example. Okay. All right, let's combine these two things together. So here's your new function. You've got y is equal to 1/2 sine of 4 theta. So notice that this problem, the value for a is 1/2. And so then the amplitude would be the absolute value of 1/2. So in this case, the amplitude would be 1/2. Miss Burrell's coming in right now. Would you like to say anything, Miss Burrell? She just said, oh crap. But it's still good. All right, so the amplitude would be 1/2. Now, the value for k in this problem would be 4. That's not my period, it's just the value of k. Remember, the formula to find your period is 2 pi over k. So you'd have 2 pi over 4, which would reduce to pi over 2. So this graph is not finishing from 0 to 2 pi. It's from start to finish. It's going to end at pi over 2. So that's how long it takes for it to complete one of its images. So now let's just do a rough sketch of this. And we ain't got to do anything fancy with it. we can just do that. It's got a maximum of 1/2. It's got a minimum of -1/2, and we know it's